Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Okay, chapter 2-6, continuous compounding. Well, what in the world is continuous compounding? We've done simple interest, which was compounding once for an entire year. Then we went to compounded interest. We did annual, which is the same as simple. Then we did semi-annual, and then we did quarterly, monthly, daily, by the hour, by the minute, by the second. Are we leading up to something here when we say continuous? Perhaps. Here is example 1. So before that, though, continuous compounding will be addressed here. Exponential base E. So I'll just say something really quick there here. If I go to my calculator, and if you notice right here over the division symbol is the letter E. So if I hit second divide, there's the letter E. And if I hit enter, that is 2.718281828. Okay, that is what they're talking about. So we'd have a base that would be 2.718281828, and it goes on and on and on and on and on, and to a certain power, because that's what a base is. Okay, so E is a number, 2.718. Okay, continuous compound interest formula. So that's what we're leading up to here. So example 1 says, given the quadratic function, as the values of x increase to infinity, what happens to the value of that function? So let's just look at it in our calculator. So let me go to y equals, and I put it in right here at y equals, because if I just do it on my home screen, I've got to enter them manually every time. So how about we just put the function in y1, and then when I want to go to my graph, here's what I'll do. I'll hit second table set, and I want my independent variable to be asked, so I can plug values in myself rather than just saying 1, 2, 3, 4, 5. So then when I go to second table, blue table, see it, second graph is table, and I plug in a 1, I get 9, because 1 squared is 1, plus 3 times 1 is 3, 1 plus 3 is 4, plus 5 is 9, and that's what you get. If I plugged in a 2, that'd be 2 squared, which is 4, plus 6, plus 5, and that's 15, and so on and so on. But if I get to a bigger number like 10, I get 135. What happens if I put 100 in? 10,305. What if I put 1,000 in? Okay, 1,000 squared plus 3 times 1,000 plus 5. I get this E. Okay, it ran out of room, so it's putting it in scientific notation. And they're only giving us the first digit, so it's not very useful. 1 point what times 10 to the 6th power. That's what that E6 means. So the calculator doesn't handle big numbers very well. So I am going to switch over to an Excel spreadsheet. And I'm just going to talk about this a little bit. Actually, it's not Excel, it's Google Sheets. So the first thing I'm going to do is I click on the top left corner. I like my font to be a special font. I like Century School Book. It just looks nicer. Okay, and then when I go into that first, actually, let's select the whole thing as well and have everything center nicely. So I clicked here to select it all. And then I clicked here, horizontal alignment, and this is center, this is to the right, this is left. Okay, left margin, right margin, center. So I'm centering all of these. All right, so now I want to put the letter X here, but I want to format that cell. I want it to be bold, format, italic, and I want the values that are in these two to have a border underneath them like so. So there it's all set up. And now if I just hit X and hit enter, there is my X, italic. And then I want f of X. I'm not going to type the function in here. And I didn't do my, so if I just, the easiest way to bring over your formatting is to just copy the cell over and then change what's in the cell. So now I want f parentheses X, and I'm done. So there is my X and my f of X. So let's put a 1 here for starters, and notice it's centered nicely. Okay, so then f of X, well, what is f of X? Well, I need to come up with a formula. So what was it? It was x squared. So it's this column over here, this cell value squared. So I would say equals this times itself. I could use squared, but times itself is just as easy. Anything times itself is squared. So A sub A2, which is column A, row 2, cell, times A2 plus, and it was 3 times this cell plus 5. So it's A2 squared plus 3 times A2 plus 5. And I got 9, just like I did in my calculator, 9. I'm just checking a couple numbers. Now if I put 2, enter, and now I just have to click on this corner and drag down. See what happened? You drag down and it brings the formula down. Now it's saying 5 here because there's nothing over here. So that's considering the table value to be 0, and 0 squared plus 0 plus 5 is 5. Okay, so let's look at some bigger numbers though. Let's look at 100 for our first number. So we put 100 in and it's 10,305. Then I'm going to put in 1,000. And this is where the calculator stopped and went to 1.0 times e to the, what was it? E to the 6. Okay, well that is 1,003,005. Okay, and the next one, let's do 90,000. We're just going to go bigger now and hit enter. And notice this number, and I'm not sure if I can format these to be, let's try. Let's format these to be, can I put numbers? Let me see, font number over here. Is there a place where we can put place? Yeah, right here. That's better. So now it's putting commas in so we can read it easier. So this is 90,000. I don't want any decimals, so let's take care of that too. So let's come down here and move the decimal 2 places to the left. And there it is. It's looking nicer already. Okay, so 90,000 squared plus 3 times 90,000 plus 5 is 8,100,270,005. Okay, now let's go to another one. Let's add a 0. 900,000. Enter. Okay, now we're up to thousands, millions, billions, 810 billion. Okay, now let's go to a really big number. Let's go to 8 million. Okay, and since the number's getting so big, I need to make my cell wider. So now we're getting up to a really big number. And then finally, we're going to do 50, enter. So 50 million. Okay, hang on. There we go. So look how big that number is getting. So to answer this question now, as x gets bigger, what is the function doing? Well, obviously it's getting a lot bigger, even faster. Okay, so what happens to the value of f of x? Okay, so what we would say here is as f of x, the function is approaching infinity, the value of f of x increases without bound. Therefore, f of x has no limit. Okay, and there's one of the key terms here is limit. Limit means that we have to stop at some point. We're getting really close to something, but never get any greater than it or less than if we're going the other way. So this has no limit. It would just keep getting greater, larger and larger and larger. So now check your understanding. It says as the value of x increases towards infinity, what happens to the value of this? What happens to g of x equals negative 5x plus 1? So pause the video, think this through. What do you think is going to happen as your x gets bigger? What's going to happen to the value of the function? So here we're going to do this in the same spreadsheet that I just did, but now my g of x it's called g of x instead of f of x, and it's negative 5x plus 1. So if I go back to this, now I would just simply call this g, like so. And then I change my value here, and it was negative 5x plus 1. So you'd say negative 5 times x, which is a2 plus 1, and hit enter. And then what's nice about this is we can now drag down our new function that we just created. And there it is. Well, what is that number doing as we put bigger numbers in? So I can just start making really big numbers and look what, and I actually have to drag this down. That's the old function that I put in. I have to drag this down to here. Okay. So what's happening to this number is it's getting bigger and bigger and bigger. And what if I added a 0 to the end of this and made it another digit higher? See what happens? Okay. And if I just keep making it bigger, how about 3 more zeros? 1, 2, 3, enter. Obviously, you can see that the numbers are getting smaller, negative. They're getting bigger in the negative direction. So the answer to that would be the numbers are getting smaller with no limit. They're approaching negative infinity. And therefore, g of x has no limit. Okay, so now example 2 says, given the function, where am I? Here I am. F of x equals 6x minus 1 divided by 3x plus 2. As the values of x increase to infinity, what happens to the value of f of x? Let's just try the calculator again for this one. So I'm going to go to y equals, I'm going to clear this, put parentheses for my numerator function, which is 6x minus 1. So that's a linear function with a rate of change or slope of 6, y-intercept -1. And then the bottom one divided by another linear function, which is 3x plus 2. Rate of change or slope of 2, y-intercept of 2. But then when we divide the 2, what's going to happen? So if I hit second graph and I look, 1 was 1. 6 minus 1 is 5. 3 times 1 is 3. Plus 2 is 5. 5 over 5 is 1. Plug in 2, we get 12 minus 1, which is 11 over 6 plus 2, which is 8. 11 over 8 is 1.375. Plug in 10, we get this, and keep going. If I keep adding on zeros, the next one would be 10,000. And that's 1.998. Let's go 100,000. And it says 2. Okay, that's not true. It will never equal 2. It's supposed to just keep getting closer and closer and closer. So if I go into my spreadsheet instead, okay, I'm not liking the results of that. Let me go into my spreadsheet. And if I had my function now, I'm going to change it. And so it's going to be parentheses for the numerator. And what was it? It was 6x minus 1. So 6 times this, which is my x, minus 1, close the parentheses, and then divide by parentheses 3x plus 2. 3 times my x is here, and that's plus 2. Close the parentheses and hit enter. So when I plugged in 100, I got 2. Let me see. Is that right? 6x minus 1 divided by 3x plus 2. So if I plug in 1, I got 1. Okay. And then I need to drag this function all the way down so it repeats. And then plug values in. So let's do 2. Is that right? Let me see if this is working right. 6 times 2 is 12, minus 1 is 11. 2 times 3 is 6, plus 2 is 8. That is not true. So this equation is not working. So I have 6x, which is a 3. Oh, I see. Yeah, that's right. A3 minus 1 divided by 3x plus 2. Why is that not working? One moment. Okay, I figured it out. I remember now when I did my last functions, I decreased my decimal, so I need to increase. Oh, there it is. Whoop. So 1.375 is when I plug into, so the function is working. It was just rounding. So now when I drag these values down, it's going to go 3, 4, 5, 6, 7, 8, 9. I need to drag out my decimals. So watch what happens when I do that. And keep going. Okay, as you can see, the numbers are getting bigger. 1.8, 1.88, 1.89, 1.9, but now we need to get numbers larger faster. So let me go back to 10 here and 100 here and 1,000 here. 10,000, 100 or a million, I skipped one. 100,000, a million. Notice what's going on here. I'm going to keep doing this. So what am I doing? I'm multiplying by 10. So how about I do equals this times 10 and hit enter. And then when I drag this down, it will just keep multiplying by 10 for me, which is pretty cool. That's what I like about these spreadsheets. So isn't that cool? So it's just adding a 0 every time. And if I now took these, looks like a tree. If I took these and made them right like so, now you can see the decimal place is only increasing by 1 every time. And again, it's saying 2, but it's 1.9999998. I find I need to go out more decimal places is what it is. So let me choose all these and add decimal place. Whoops, what did that just do? See what happens when I extend the decimal places? Let's make this really large and I'll keep doing it. Okay, it's not going to let me go any further than that, but it's doing better than the TI calculator does. It got us all the way down to here and it was 1.9999. So it just won't go out another decimal. But what actually would happen was this would become a 9 and this would become another number like 8. And then these 3 shouldn't be going away. It's rounding. Okay, so eventually, but what this is I'm trying to get to here is this thing is getting closer and closer to 2, but it's never going to get there. It's going to be 1.999 repeating out to infinity, and then a number smaller than 9 at the end. Okay, so what it's doing is getting closer and closer to 2. Okay, so how I would answer this, it would be, I would say, it's called a limit. The limit as x approaches positive infinity, as I put bigger and bigger numbers into this function, the function equals 2. It's getting closer and closer to 2. So that's a limit. So the function's approaching 2. Okay. So now it says, check your understanding. If f of x equals 1 over x, create a new table and use your calculator to find the limit of f of x as x approaches infinity. That's how we say that. So you would say the limit as x approaches infinity, f of x equals what? So if I now do that, I'll use a spreadsheet. And if I go into my spreadsheet and just change that first function to 1 divided by this. Okay. Okay, so back at it. Had to change my shirt if you didn't notice. And so I put in 1 divided by a sub 2, which is my x. So I put that here. And then when I drag that function down the rest of the way, as that number gets, as x gets bigger, f of x is going closer and closer to 0. If I kept going, this one would keep moving this way, and we're getting closer and closer to 0. So when I go back to my thing here, and f of x, the limit as x approaches infinity, f of x equals 0. Okay. Okay, example 3. Another function, f of x equals 2 to the power of x. Find the limit as x approaches infinity of f of x. So what they mean is, as x gets bigger and bigger and bigger, what does the function do? So if I go back to my spreadsheet and I change that equation, so I'm going to come back here and erase that 1 over x, which was the last one, and it said x. So now our function is 2 to the power of x. Our base is 2, so I'll put 2. And to get a power, I'll use the caret, shift 6. And I want it 2 to the power of a1, or 2, I mean, a sub 2. So there it is. And I hit enter. So 1 to the 1 or 2 to the first power is just simply 2. And then of course, what's 2 squared? That should become 4, and it does. And I can get rid of my decimals now because we're not going smaller, we're going bigger. So let's get rid of the decimals like so. And actually I want to now drag it all the way down like so. Oops, I did it wrong. Okay, so let's just grab the first one, drag it down. And okay, I didn't do it wrong. I'm just going in multiples of 10, and that's just way too much. So there we go, 2, 4, 8. So 2 cubed is 8. So then if I just grab these two and increase by 1 every time, and let's make this column over to the right. Okay, and what's going to happen if I now take this last row and drag the rule down? I missed it. Undo. Okay, and redo. Grab these two, grab the corner, drag. And if I go out, I don't know, this far out, and it didn't do it, what am I doing? Let's see, go back up here. I want to take these two, drag them down. Hopefully this does it. There we go. So as you can see, this number gets really, really big. So 2 to the 24th is 16 million. 2 to the 35th is 34 billion. And as you can see, it just keeps getting bigger and bigger and bigger. So the answer to that is it's never going to stop growing. So we're going to say the limit as x approaches infinity of the function f of x, where f of x equals 2 to the power of x equals infinity. Okay. And now it says, check your understanding, given the function f of x equals 1 to the x, find the limit. So I would say the limit as x approaches infinity of f of x equals. Now, before you go running to technology, think about what they're asking first. So here's the function, 1 to the power of x. What happens when x gets bigger? Well, what's 1 to the first power? 1. What's 1 squared? 1. What's 1 cubed? 1. No matter what I plug in, the answer is always going to be 1. So that's our limit. Okey-dokey. Okay, example 4 says if the function f of x equals 1 plus 1 over x, and you take that sum quantity to the power of x, what is the limit of the function? So I would say the limit as x approaches infinity. Now we already calculated one of these. Okay, the limit of a constant is of 1. I mean, no matter what, there is no x. So the limit as x approaches infinity of 1, well, there's no place to put x. So the limit as x approaches, the limit of 1 to the power of x. So what we're going to do is we're going to take this power and we're going to distribute it. Okay, so 1 to the x is 1. We just did it on the last example, or the check your understanding. The limit as x approaches infinity of 1 to the x is 1. And then the limit, so if I say plus the limit as x approaches infinity of 1 over x to the power of x equals, well, the limit not to the power of x, let's just do the 1 over x portion. The limit of 1 over x we just did on the last page. Or was it 2 ago? 1 over x is right here. The limit as x approaches infinity of f of x is 0. Okay, so the limit as x approaches infinity of 1 over x equals 0. So we're going to put 0 here. So if we're going to take the limit of 1 to the x is 1, and the limit of this is 0, then the limit of x from x to as x goes to infinity of 1 plus 1 over x is going to be the 1 plus 0, the sum of the limits. So there's a thing that we say, the limit of the sums is the sum of the limits. What's 1 plus 0? 1. So if I put this in a graphing calculator or in my spreadsheet, it would go to 1. All right, so now it says set up a table in your calculator to find the limit of this, round to 5 decimal places. Okay, so let me. Okay. All right, so we're going to put this in our spreadsheet. Limit as x approaches infinity of this function. Now, I forgot the power of x in class, so I'm not going to forget that here. 1 plus 0.05 over x. So I'm going to go to my spreadsheet, and I'm going to get rid of that 2 times a. So it's going to be parentheses 1 plus, and it's 0.05 divided by x. And in our case, in this, it's a sub 2. 1 plus, I'm going to do another parenthesis for the fraction, 0.05 divided by a2. Close the parentheses, close those parentheses, and do the power of, so that's the caret, and we're going to use a sub 2 again. So let me check that again. 0.05 over x to the power of x. 1 plus 0.05 over x to the power of x. And I hit enter. 1 is 1, and then I drag my function down. It said to round to decimal places. So this number is getting small. So let me just drag this down first, and you see it should change eventually. Maybe I need to make my numbers get bigger faster. So how about I double it? So let's say this equals this times 2, enter. So now it's 4, and then it will continue that way. This should become 8. There we go. Now we're doubling it. Click on this, drag it down. Now, if I, let me see if that's right. Click on this. 1 plus 0.05 divided by x to the power of x. Is that right? 1 plus 0.05 divided by x, all to the power of x. Let's look at decimals. Let me go out the maximum it'll allow me. And then I'm going to drag this rule down. Okay, so I guess I had to pause it for it to work right. So I re-punched that in, and I have the 1 plus 1 over x to the power of x again, and there's my 2, which is what it should have been. And then I'm going to drag this down. And I'm going to go way out to infinity if or close to it. Why did that not change? Why did it go to 1 here? It should not go to 1 ever. Interesting. How about I do this? Delete. Okay. So what this is doing is saying 2.718 to 818, 2.718281828, and it says round out to 5 decimal places, so it's 2.71828. Okay, so what we will say is f of x, no, limit as x approaches infinity of 1 plus 0.05 over x to the power of x equals 2.71828, rounding to 5 decimal places. Okay. Now, if I go to my graphing calculator, I want to point something out to you. If I hit second E, okay, E is above the division symbol, and hit enter, it's 2.718281828, and it just keeps repeating, and that is what we got. So that equals the number E. Okay, so that's that one. Okay, so before I do this one, E is the exponential base. That's what it's called. Really important number in math, the exponential base. So now example 5 says if you deposit $1,000 at 100% interest compounded continuously, what would your ending balance be after 1 year? Okay, so this would be like taking the limit as x approaches infinity of that $1,000 principal and multiplying it by 1 plus 1 over x to the power of x. And that would equal 1,000 E. Okay. Okay, so what's happening here is if we look at the compound interest formula, A equals principal times 1 plus R over N to the power of NT. What do we have here? That's what we have. 1,000 is our principal. Our rate is 100%, which is 1, divided by N. Okay, well, N is an X that's going to go to infinity, because it says compounded continuously. So is it is it once a year? Is it once a month? Is it once a day? Is it 300? Is it once an hour, once a minute? No, it's compounded continuously. So that would take us to an X that goes to infinity. So it's 1 over N to infinity, which would become what we just did on that last example. 1 plus 1 over X to the X is E. The limit of it as x goes to infinity, that becomes E. So then my answer is going to equal 1,000 times E, which is, and if I go back, E was what? 2.71828. So 2.71828, and the decimal was here. 1,000 moves it 1, 2, 3 places to the right, and you'd end up with $2,718.28 after a year at 100% interest. You would more than almost triple your money. Okay, so now check your understanding. The irrational exponential base E is so important in mathematics that it has a single letter abbreviation E and has its own key on the calculator. So when I showed that in class, E is, well, I didn't get to that in class. E is right here. It's above the division symbol. So turn your calculator on clear. You hit second and E is blue. So that tells you to use the second button. And you hit enter and there it is, 2.71828. Okay. So when you studied circles, you studied another important irrational number that is a single letter designation and its own key on the calculator, and that is pi. Pi is 3.141592654, and that goes on forever and ever. So it says use the E and pi keys on your calculator to find the difference between E to the pi and pi to the 0. So E to the pi equals, and pi to the E, that's not a 0, because pi to the 0 would just be 1. So E to the pi, so I'd do second E to the power of, and pi is that caret button, second caret E to the pi equals, okay, and it's an approximation, so let me do that. and it is it's 23.14069. Okay, is there more? 069263. I'll just show what the calculator did. Okay, and then I'm going to do pi to the e. So it's going to be second pi to the power of second e, enter, and we got 22.45915. Oops. 5915772. Okay, and the number was okay. So now it says use e in the pi to find the difference, round to the nearest thousand. 10th, 100th, 1000th is right here. That would become a 1. 10th, 100th, 1000th is right here. So this is 23.141 and this is 22.459. Okay, so I just wanted to see which one was larger so I don't get a negative. So now I'm going to take e to the pi, second e caret second pi, get out of that power, minus pi to the e. And the difference is 0.682. Okay, and that is the difference, 0.682. Okay, and I'm going to bring something that's pretty interesting. So it says the answer is 0.682, which we got, and it says if any students have encountered the golden ratio, point out that it also has a letter designation, the Greek letter phi. Okay, so there you have it. Okay, so here it is. I went to Google. The golden ratio is 1.6180339. So there's phi, and it's 1 plus the square root of 5 over 2. And that gives us this irrational number, the golden ratio. And it has a lot to do with uniformity in nature. Pretty interesting stuff. Okay, example 6 says if you deposit $1,000 at 2.3% interest compounded continuously, what would your ending balance be to the nearest cent? So I'm going to write this in as a formula now. The limit as x approaches infinity, that's what we get for continuousness, okay, of our principal times, and it's going to be 1 plus r over our x, in this case, to the power of our x. That's the formula. So then we substitute in our givens, the limit as x approaches infinity. So off to the side here, like we've always been doing, the principal is 1,000. The r is 0.023, and x is always going to go to infinity, okay? We're always going to go to infinity with x. So what's going to happen is it's going to be the limit of the principal times 1 plus 0.023 over x to the power of x. Okay. All right. So continuous compounding interest, well, this is E. Okay, so then we have an R, and then we also have a time going on here, how frequently that's going to happen. So the continuous compound comes from this limit formula, and it's going to derive, it's derived from the limit formula, and it's going to be B for our balance, ending balance, and it's going to equal the principal times the base E to the power of RT. So we always say PERT. Okay, it's the PERT formula. So we have P. We ease a constant, it's 2.1718 and so on and so on. R is our rate and T is our time. And in this case, it's 5 years. Okay, so we're going to say the balance is going to become our principal, which is 1,000 E to the power of R, which is 0.023 times 5. So B is going to equal, we get our calculator, and we're going to say 1,000 E second divide to the power of 0.023 times 5 and hit enter. And we get 1121.87. So $1,121.87. So this is new to us. This is the formula for continuous compounding continuously. P times E to the RT. So now it says check your understanding. Craig deposits $5,000 at a 1.12% interest, compounded continuously. So there's the key word right there. As soon as you see that, B equals PERT. It's really easy to remember. So we need P, we know what A is, we need R, and we need T. Principal is 5,000. Interest is 0.0112, our interest rate. Compounded continuously is our base E, and our time is 4. So B equals 5,000 E to the 0.0112 times 4. So that is going to give us, when we put that in the calculator, 5,000, not 50,000, 5,000 E to the power of 0.0112 times 4, 1.12%. And we get 5229.09. Okay, and that is continuous compounding.